Yes? Up to here? Yeah, everything is okay, everything is fine. Okay. So we were up to this point that we knew how to do the forward kinematics for 3. We had this kind of equation, the product of exponentials, all the, I don't think we use I, but it doesn't matter. As I equal 1 to ki. These were the common ones. And then we had the product of exponential ij, j, sij, I equal k plus 1, ki plus 1, 2, and I sorry, kj, kj plus 1, 2, and j equal 1 to b were the number of branches, and I okay, and this has to be equal to the desired positions, and the k would go here, right? So the angles would be different. K equal to 2 to m. Okay. Whew. So that was, and this is a bad marker. That was the general expression on, we say this transformation of each of our branches in the vector has to be equal to each of these. We need to put the j, right, somewhere. And I don't know where the j was, but we can put it up here. Each of these will be for a given in the vector, right? So you have one position for each end of the vector, and then for each of the frames that we are considering, right? So these are the design equations, and then we had a formula and then we had to count for m max. We did that for serial chains. Now we need to see how we account for m max for 3 topologies, the maximum number of positions. So what we are going to do is we are going to do it, actually I can give you the formula if I have it. Here it is. For 3 topologies. And remember, we are talking about trees which are already compacted and reduced, basically reduced, so we don't have loops inside, okay? And we talked about that reduction for a couple of days. This is what we have. M equal to dse dot e minus, and I'll tell you what these are. N dot b divided by d e n dot b minus d g a dot e. Okay, plus 1. Now I have to remember what these are. That's not going to look very nice. So these are basically vectors that you can derive from your graph matrices, okay? Where, all right. The D, E, J, these are the degrees of freedom of each edge, okay? Oh, okay, let me just put this. DHE equal to degrees of freedom of each compacted edge. And unfortunately, the current version of the paper has some mistake in that equation, some typo that we need to fix. hopefully the journal where it's being published will let us fix that. We are not sure, but we will have a version, author version in our webpage with the right formula. We just had this switch in the formula. These things always happen when you publish something. Yes. Okay, so that's are the degrees of freedom of each compacted edge. It's a vector. It's a the number of edges E times 1 vector, and this is E being the compacted ones. Okay, you can do this analysis with the non-compacted graph too. It's just, it's much bigger and you don't win anything in doing that, so compacted makes it a little bit simpler. And then we have the D E S, which is equal to the number of structural, so each of the entries, okay, number of structural variables per edge structural parameters per edge, right? So this is again is a E times 1 vector. So for instance, what does that mean is if your edge, your joint is a revolute joint, you have 4 structural parameters which are independent. It's a prismatic joint, you have 2 structural parameters. If you have a compacted edge which has 3 revolute joints, you have 3 times 4 equal 12 structural parameters on that edge, right? We will do an example, so that will be easy. All right. Then we have these other vectors, D, N, E, E. This is for n the vector. This is the degrees of freedom of each n the vector. What that means is the dimension of the linkage locus space for each of them. Okay? So if this n vector moves in the whole, or it's able to move in the whole 6D space, or 6D space, then for that particular edge, and the vector, you will have 6 as your value, right? So this is a, how do we call it? Number of branches, B times 1 vector. And then we have the last one, dnc, which is equal to, these are the extra constraints, the number of constraints that you add for each branch, okay? Extra constraints each branch. When we do this counting, we don't really need to assign the constraints to a particular link in the counting, just to a particular branch. So it's a B times 1 vector again. So basically the ones that have an E on top, that means those are unknowns, and the ones that have an N, those are basically the equations you can create. Okay. And now we are missing this B and this E. And this B is a vector of ones for the branches. And E is a vector of ones for the edges. Edges. Yes. B. Ones. That means it's all ones. If you have 4 branches, you have 1, 1, 1, 1. Okay, so this is B times 1, and this is E times 1. E times 1, yeah. This is so that you can just assign the numbers to each one.
You should do 1 times B, because...
Okay. Rows times columns. This is a dot product, okay? There is always a convention, but we will consider this just vectors of And in the paper we have this in matrix form with the transpose, but here what I'm using is just the dot product of vectors, okay? Which is of course equivalent. All right. Let's do an example to see how this works. And I was just looking at this and wondering if we can just do this with the vertices. If we can just make a vector of vertices where you just have ones when you have your end effectors basically, and but that will require to modify those. So. And that makes sense only for the end effectors, not for the vertices. So that one makes sense for each vertex, but we'll leave it like that. Okay? So we are doing the same method. It's equating the number of unknowns to the number of equations and solving for m. So let us just do an example as soon as you guys. So let us do our example, the same one that we were doing. It's a very good example to use. So let's go to, and I'm going to put the compacted graph. We had a 2R serial chain here, then we had a 3R finger, and then we had another little extension of the palm, let's say, and then we had 3 fingers of 2 revolute joints each. 2R. Right? Okay, and we call this was branch 1, branch 2, branch 3, branch 4, 4 branches, and let me see, we call this guy 0. I guess that's okay, just the name. So 0, 1, 2, 3, 4, 5, 6. We have 7 vertices in the compacted graph. And then 1, 2, let me just put them in circles so that 1, 2, 3, 4, 5, 6 edges. And that, when you have a compacted graph, the number of vertices is the number of edges plus 1. So that works for us. Let's do the matrices of these ones. I don't know if we already did, but let's just do them again. So the reduced, compacted, end effector, path matrix, and that's T sub C. And now we are going to put the branches or the end effectors 1, 2, 3, 4. 1, 2, 3, 4, and then we are going to put the edges that are involved in 1, 2, 3, 4, 5, 6. And now we have to look at, in order to arrive to each of the end effectors, what edges you have to go through. Okay, so so for the first one we have 1 and 2, right? So 1, 1, 0, 0, 0, 0. For the second one, 1, 3, 4. 1, 3, 4. For the third one, 1, 3, 5. 1, 3, 5. And for the fourth one, 1, 3, 6. 1, 3, 6. And let's do the reduced incidence matrix, that is which edges are incident to vertices All right, and that's our B compacted, of course. And in this one we put the edges on top, so 1, 2, 3, 4, 5, 6 edge, and the vertices here 0, 1, 2, 3, 4, 5, 6 vertices. Okay, and now we look at, so for vertex 0 we have only edge 1, so 1, 0, 0, 0, 0. For vertex 1 we have 1, 2, and 3. 1, 2, 3. For vertex 2, just 2. Say that again? What it says here, it says edge. Yeah.
No, please. How the matrix system?
So in this case you have the edges here and the vertices here, and you look for each vertex which edges are connected to that vertex, for instance. So for vertex 0 we have edge 1. For vertex 1 we have edge 1, 2, and 3. So you put a 1 whenever you have an incidence there, so a connection. For vertex 0, 1, 2, now it comes 3, so this is a little bit, we'll need a bigger matrix. But for vertex 3 we have 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. For vertex 4 we have just 4. 3, 4, 5, 6. For vertex 5 we have just 5. And for vertex 6 we have just 6. And then you can look at whether you have a binary edge or not, or a binary vertex or not, just by looking around. So of course all the edges should be binary, because that's the way we have compacted that, right? Or we have reduced that. And then in the vertex you have the degree of the vertex just by reading across. Okay. All right. Now we need to start working on those matrices. We actually use this later, and I should use it today. Let's start computing these vectors. D, E, S. And that was what? I forgot. Number of structural parameters, right? Per edge. How many edges? 6. So this will be a 6 by 1 vertex. So the first edge here has 2 revolute joints, which means 8 structural parameters. Each revolute joint is 4 structural parameters, and we are putting just the independent. What are the structural parameters again? The Plucker coordinates of the line defining the joint. That's what we want to find out, right? Let me just maybe make a note here. Structural parameters. S plus epsilon S0. These are our unknowns. These are 2 3D vectors, so they are 6 per joint, but we know that this has to be unit, this times this is 0, so there is only 4 independent ones for each joint. Edge number 2, 3 revolute joints, 12. Edge number 3, 1 revolute joint, 4. This is 2, 2, 2, so it will be 8, 8, 8. So the sum of all these elements in your vector should be the total number of structural parameters in your whole tree structure.
Multiplying it by 4? Multiplying it by 4?
This one?
Yeah.
This is for this edge. It's only a revolute joint. Single revolute joint, yeah. Yes? So remember, this is what we don't know. We are doing a design problem. This is where are our joints? Okay, where do we need to locate these joints in order to do this task? So these are all our unknowns, which are just line coordinates. That's what they are, nothing else. Let's do the D, E, J. This is the number of joint variable.
The D is for each age, right?
Yes. Yeah. I don't know actually. It should be age, right? Well, some of these things, but then the end doesn't really mean anything anyway. Actually, anyway, let's just say it comes from age. Age. I think it's easier to remember if we do that. Okay, so these are the degrees of freedom, J, of each edge in the compacted case. 2 revolute joints, 2, right? 3, 1, 2, 2, 2. Here, if there is some relation between these joints, for instance, if they are coupled, you can just put that there. So for instance, imagine these 2 revolute joints are coupled with a cable and they move with the same angle every time. Then you only have 1 independent variable, so you would put a 1 there instead of a 2. Okay. So these are basically joint variables for each compacted. And of course, another thing that we haven't, if this was a spherical joint here, then it has 3 degrees of freedom each. So that will be a 3 instead of a 1, right? So you have to count how many degrees of freedom your joint has. If these were 2 cylindrical joints, that will be 2 degrees of freedom each. That will be a 4 instead of a 2. All right. Next one, the DEEN. DEEN. And that we said is this was the dimension in which each of these end effectors move. These are revolute joints, and we know that as soon as you have one revolute joint, the linkage locus space becomes the whole space, which means that for each of them, this is 6. Each of the fingers moves in our 6 degree of freedom space. We don't have planar fingers, we don't have specific conditions on that. So space in which each of the end effectors move. Each end effector moves. Okay. And then the last one, which was which one are we, the DNC, right? DNC. And that was the extra constraints. In this case, we just don't put any extra constraints. You could say, but I want these 2 revolute joints to be parallel or perpendicular to mimic more like a wrist. Or I want, for each fingers, I want to look like a human finger, so the joints have to be parallel. In this case, we just design a general hand or a general tree structure with no conditions, which means 0 extra constraints for each of the number of extra constraints. Number of extra constraints. If you have extra constraints, then you have to add those as equations to the one that is erased here, to our system of equations, right?
If it is in like a human finger, then suppose it is like one finger is like a human finger, then how will we define that concept?
So for instance, if this is, and here we don't have the names, but imagine this is, so here you have 2 revolute joints, S1, S2, S3, S4, S5, S6, S7, S8. So you would say that S7 and S8 are parallel, right? That's the way it would be. So you would say S6, S7 are parallel, and then you could impose conditions of parallelism here based on line geometry. So you would do the dot product of them, and then you should get S6 dot S7, and you get a dual number there, right? Cosine of the angle between them minus epsilon A sine of the angle. Remember the dual geometry, when you do the dot product of 2 lines, you get that. So if what you want is this angle to be 0, right? So cosine of alpha equal 1. So you would say S6 dot S7, the direction vectors, equal 1. Okay, that means they are parallel. Alpha equals 0. Let me just write that again. So here you have S6. In general, they are skew. And then you look at the common perpendicular line, right? And then when you do the dot product of this, you get the cosine of the angle between them, and then minus the length times the sine of the angle between them. That's what the dual dot product gives you. So using the dual dot product and the dual cross product, you can impose conditions on relative location on an angle between lines very easily. And these are units, so that means alpha equals 0 or alpha equal to pi, which is also acceptable, right? So you will have this extra bilinear equation. These are all unknown. So you would, this will be S6x, S7x plus S6y, S7y plus S6z, S7z equal 1. So that's one more equation for your system of equations, and then 1 equal here instead of 0 you will have a 1 more equation. Okay.
On that position will be 1
here, because this belongs to this second branch. We have imposed this in these two joints. Okay. Right now we don't have any, but this could be a possible constraint. And of course, if you have these constraints, and especially if you actually give real, instead of adding equations, you give actual numbers to some of them. So for instance, you say, okay, I want this joint to be along the z direction. Then you simplify your system, and you have less equations. You have more limited set of solutions too. But in general, in the phase that we are right now, which is beginning this something new, we want to see what happens when you have this as the most general case. How many possible solutions you can get if you don't have any extra constraint. Once you understand this very well, then you can start adding constraints and making something that may be more useful. All right, so we have these vectors, and then we have the vector E, which was the vector of number of edges. So how many edges do we have? 6, right? Again. So 1, 2, 3, 4, 5, 6. And this vector at some point when we do subgraphs then won't be as easy, then won't be a 1, all ones, okay? Right now, because we are considering the whole graph, all ones. And then the number of branches, so we have 4 branches, 1, 2, 3, 4. Now we plug that in the formula, we just turn the crank, and we get M equal 5. And that, remember, that means for each of the end effectors we can define 5 points. In principle, it seems like. The meaning of this is we can define up to 5 displacements for each end effector. And that means simultaneously, okay? Why are they simultaneous? Because we have some common joints, okay? So once you have an angle for this joint, that is going to be the same for all of the end effectors, right? B. This is the number of branches. So 1, 1 in you have 4 branches, you will have 4 ones. 1, 2, 3, 4.
Oh.
Okay. Yeah, these vectors are kind of simple now, but they won't always be. And this is the number of edges. So how does it feel this? for your intuition. It kind of makes sense, right? Because you have 2 joins here and 3 here, so total in this branch is 5, and then total in this branch is 5. Each branch has a, so maybe this is right, maybe. But we have accounted for everything at the same time. And we will see next day that actually you can have subgraphs. So the fact that we define this doesn't mean that each branch has 5. Now we have to check, make sure that we don't over-define or under-define one of the branches. So we need to look at each of the subgraphs separately. Do the same thing for each subgraph. Not only that, but it turns out that because now we have several element effectors, we can actually change the root. For instance, now we fix this and move all these other ones. First we were like this, and now we fix this and we move everything else. And that may change the solvability too. So we need to look at all permutations of root, vertex, and then all possible subgraphs for each permutation.
So is that by coincidence that we got the 5 R's?
Well, yeah.
The branch will have 5.
Yeah, so in general, if you have a 5R, the number of positions for a serial chain is more than that. It's, what is it, 21, right? It's a lot. I think it's 21. So just the fact that some of them are common reduces your number of positions. We get this number. We need to make sure that this is right by checking now the subgraphs. Okay. If we see that if everything works well and it's solvable, then we can define this. If not, we may be over-defining or under-defining. In this case, intuitively it seems that it will work, but we will check more. You would define. It would be 20 positions, right? 5 times 4. 20 positions. 5 per finger, or let me just say per end effector. Doesn't have to be hands, could be. Another application we were thinking of this is just consider this instead of being fingers, they could be legs, right? You could perform locomotion and look at your root as being your moving system, and then these are the feet instead of being the fingers. 5 per end effector. All right, and then create relative displacements. And how do we do that? We select one of those as our reference. It doesn't matter which one you select for the design. Selecting one position as reference. So now we will have 4 per finger, so we'll have 16 positions. Okay. And now we write the equations. Oh man. Equations. And those will be, so the 16 positions will look like this. P, I forgot what letter we use. P1KJ. P1KJ. And these are displacement. Remember, either a 4x4 matrix or a dual quaternion, whatever you want to express your displacement. Where, I have to see my notation. J is the number of branches, and K is the number of positions. So K equal to 2, 3, 4, 5 is the number of positions. J equal 1, 2, 3, 4 for the branches. Right? And now we write the equations. So for this case, we have P1KJ. Let me just write this. E delta theta 1 S1 delta theta 1 k 1 2 1 3, yeah, for k, e delta theta 2 k s2. Now we are going to do this one. E, so this will be, actually this will be for branch equal 1, so that means I should have j equal 1, so this is for branch 1. E delta theta ij j 3 1 or 1 3, I forgot how we did that. 3 1 k over 2. No, I don't know if it's 3 1 or 1 3, but that means branch and join. 4 1 s 4 1 e delta theta 5 1 s 5 1 k, that means for position k equal 2 3 4 5. This will be for branch 1. And then we will have a P1K2 equal 2, and then we will have the values for 2. This one will be the same, thetas. And then let me just put the second one too, and that will be enough. Delta theta 1K over 2 S1 E delta theta 2 over 2K S2. Now we have this one, which is now common, E delta theta 3K over 2 S3. And now the ones that are not common will be 4 and 5, delta theta 4 2 over 2 S4 2, E delta theta 5 2 over 2 S5 2, K equal 2 3 4 5, branch 2, and then we will have a P3 and a P4. That's if we have extra constraints, we will add them to the system. If we don't, then that's the whole system, which is as big as 4 times 4 16, right? So number of equations are 4, because we have 4 branches, times 4 for each, times 6 components independent for each of them, whatever that is. What is that? Ninety-six equations. 96 equations. This is assuming that this number is correct. We need to check the subgraphs, okay? We will check that next day. .96 very nonlinear equations. Yes, go ahead.
Yeah, for Pik3, the next equation.
Yes.
There will be del theta 4 by 2 is 4.
Yes.
3, right?
So this one will be common. Let me just write one more. And then the next one will be 3 4 exactly. KS2. E delta theta 3 over 2 KS3, and now we have branch 3. So delta theta 4 3 is 4 3. E delta theta 5 3 is 5 3. This is just different notations. And the next one will be the fourth branch, so this will be 4 4 5 4. 96 equations, very highly nonlinear equations, almost impossible to solve, okay? Now you just put this in your solver and let it split solutions. There are many solutions in general in these problems. In fact, it's hard to get the same solution twice. Now, once we have done the subgraphs, we will start doing examples, because this is all very theoretical. You really need to see the designs now. So our tricks will be ready for us. Send to solver. Hopefully our tricks will be ready for us.
It's not ready.
You can use any other solver that you want, okay? But in the advantage of this is you just R-Tricks, you just give the positions, and then you give the graph. So you say this. Well, how did we do that? We have 2 and then 2 branches. One was 3, 1, 2, 2, 2. That was this tree, right? You just give this topology to R-Tricks, and then on the positions you want to reach, it assembles the equations itself and sends them to the solver. So you are, saving a little bit of an effort. Not only that, but yes.
Sorry. That should be theta 4 3 or theta 4.
This one? 4 3 means the fourth joint of this branch in branch 3. Branch 3. So you have 1, 2, 3, 4, and 5. 2 more joints there. Yeah? And I'm not sure what I don't know if it's 3 4 or 4 3. I'm just it may be switched in our official notation. I don't have it now, but in any case, one denotes a branch, the other denotes if you count only that branch, what's the serial the number in the serial chain where it goes basically. So let me erase this, which belongs to the previous slide, and then I'll leave this ready for it to be taken.